Hi, and welcome to Unit 5.3. In this unit, we're going to use the value for K to determine the amount of reactants and products at or before equilibrium. So in 5.1, you learn how to calculate the value for equilibrium constant and also how to write the equilibrium constant expression. And in 5.2, you applied that knowledge to determine or predict the shift of reaction by comparing the value of K to Q. Now we're going to apply our equilibrium constant to determine how much reactants and products exist before, during, and after equilibrium. For us, we're just going to look at examples like once equilibrium is established, but just note that the skills that you learn here can be used for other cases as well. All right. This video is really just a bunch of word problems. So the general approach we use for tackling word problems is analyze, plan, solve. And when you analyze, you're sort of like reading the problem for key information. And then when you're planning, you're like sort of setting it up so that you can then do the solving part. That's sort of the general steps. So if you want to take a moment, pause the video, sort of read through some of the things that we look at when we're analyzing, planning, and solving for these specific problems. Okay. So what we're going to be doing is we're going to be given like amounts or values, and we're going to use the K expression to determine a value or concentration or pressure of either a reactant or product that's our unknown. So let's look at this first example. It says for the Haber process shown above, which is this reaction, Kp is equal to 1.45 times 10 to the minus 5 at 500 degrees Celsius. In an equilibrium mixture, the partial pressure of H2 is 0.928 atmosphere and that of N2 is 0.432 atmosphere. What is the partial pressure of NH3 in this equilibrium mixture? Okay, so what are some pieces of key information? One key piece of information that I see here is the equilibrium constant, Kp. So whenever you're dealing with equilibrium, think of an equilibrium constant, you might want to underline that. The other thing that they tell me that's super important is they tell me that the reaction is at equilibrium. That's going to be helpful because if you know that the reaction is at equilibrium, that means that the values that they're giving you are the values at equilibrium. And that eliminates the needs for an ice table. So in this case, it's actually going to be quite simple, just a plug and chug, because they're giving me the equilibrium pressure of H2 and equilibrium pressure of N2. So I can plug that into my equilibrium expression. And the one I don't know is the equilibrium pressure of NH3. All right, cool. So the first thing I did here was I just sort of like analyzed it for key information, which includes the constant, the equilibrium constant, also knowing that the reaction is at equilibrium, so that tells me I don't need an ice table to solve, and the partial pressures of H2 and N2, and what I'm looking for, which is the partial pressure of NH3. Okay, so now we can move on to the planning and solving part, and this part is just so super neat because you've already practiced all these things already. So I have my value for Kp, I need my expression for Kp, so let's go ahead and put that up there. We know that Kp is just going to be the pressure of the product, so the pressure of the reactants. Of course, you're going to raise everything to the power of its coefficient. So the pressure of NH3 squared over the pressure of N2 times the pressure of H2. Now once I have that, I can just go ahead and plug in all this information that I've got. So my Kp, I can plug it in right here. My pressure of equilibrium pressure of H2, I can plug it in here, and N2, I plug it in there. And so I get this sort of thing that I have. So since I have a fraction, I can use my cross multiplication to sort of multiply first I'll multiply these two terms, and then the product I get from that, I'm going to multiply it with the 1.45 times 10 to the minus 5, and I can set that equal to pressure of NH3 squared. So that's what I got now. Then to solve a pressure of NH3 squared, I'm just going to take the square root. And that's that. It's just an algebra problem essentially. So it's straight plug and chug. All right, so you've seen this example. I want you to try it with this CFU. So you want to analyze it just the way that we did before, looking for key information, write that key information out, write out your Kp expression, plug and chug and solve. Pause the video now. When you press play again, the answer will be revealed. Okay, so I hope you use the space that was provided to solve, and let's go into the answer. So this is what your work sort of should look like here. They gave you the KP. They tell you the equilibrium pressures of PCl5 and PCl3. And you need the equilibrium pressure of chlorine gas. And so you can go ahead and once you have your equilibrium expression, you can just go ahead and plug that in, cross multiply, and solve. Okay, so now we're going to look at some other examples where, in this case, it's going to be a little bit more tricky. So in this example, they tell you a 1 liter flask is filled with 1 mole of H2 and 2 moles of I2 at 444 degrees Celsius. I think in yours it says 448, so you go ahead and change that. The value of the equilibrium constant Kc for the reaction at 440 degrees Celsius is 50.5. What are the equilibrium concentrations of H2 and I2 and HI in moles per liter? So let's sort of start at the end here. We're needing to find the equilibrium concentrations of H2, I2, and HI in moles per liter. That means we don't know the equilibrium concentrations. So what did they give us exactly? They gave us some values. They gave us the moles of H2 and the moles of I2. So that information is useful, but is it at equilibrium? And it turns out it's not, because they're not telling us that the system is already at equilibrium. So this would be considered sort of our initial amount. And initially we're starting off with some amount of both of our reactants, but we have no products. So what we need to know is, like, once equilibrium is established, how much reactants we have left and how much product did we make. The other key thing to note here is that they're giving us the value of or the amounts of H2 and I2 in moles, not in molarity. But the cool thing is they gave us the volume, so we can calculate the molarity by taking the moles and divided by the volume. So I'm just going to underline some of the key information that we sort of found here. Of course, they also gave us a Kc, which we definitely need. We need the equilibrium constant, and it's 50.5. And what we're looking for here is the equilibrium concentrations of H2, I2, and HI in moles per liter, which is essentially molarity. So here's all of the information that we got. Initial concentration of the two reactants, and what we need to find equilibrium concentrations. So how do we approach this problem? This is where the ICE table comes in handy. You may remember what the ICE table stands for. Some people call it the rice table because for the very top row, you're writing down the reaction. So H2, I2, and HI, they each get their own column. All reactants, all products get their own column, as long as they're a gas or aqueous. If it's a solid or liquid, you can leave it out. The next row has the I, which stands for initial value. So for I, they tell us initial values of H2 and I2 are 1 moles and 2 moles. And since the volume is 1 liter, that means that the molarity will also be 1 molar and 2 molar. So these values here are the molarities. And HI, on the other hand, we're starting off with none of that. So its initial molarity is 0. The next row is change. C stands for change. So what's the change? When you start off this reaction, you have all reactants. And when equilibrium is established, are you going to have the same amount or more reactants or less reactants? Well, you're going to have less because you're going to use up those reactants to make the product. So you know that the change is going to be negative something. But what is it going to be exactly? So in this case, since the coefficient in front of H2 is 1, it's going to be minus 1x or just minus x. And the same thing for I2, the coefficient in front of it is 1, so it's going to be minus x. On the other hand, our product HI, we're going to increase the amount of HI we have. So the sign for the change is going to be positive. And since the coefficient in front of HI is 2, it's going to be positive 2x. So you're going to use the coefficient in the balanced equation to determine the coefficient that goes in front of x. And you're going to use your understanding of what's happening during the reaction to determine the sign. If you're gaining something or creating it, it's going to be positive. If you're losing it, it's going to be negative. Finally, for the equilibrium part, you're just going to combine. So for equilibrium, it's going to be like 1 minus x, and that goes in the equilibrium for H2. For I2, you start off with 2. You're losing x amount of it, so it's going to be 2 minus x. And for HI, you're starting with 0 and you're adding 2x to it. So it's just going to be straight 2x. Okay, so now we have our equilibrium values for H2, I2, and HI, but there are no numbers there. In order to get the numbers, you need to solve for x. And that's where the solving comes in. So here's all the information that we have so far. We have our Kc. We know from our ICE table the equilibrium concentration of H2 is 1 minus x, for I2 is 2 minus x, and for HI is 2x. So how do we solve it? The first thing we're going to do in solving it is we're going to set up our equilibrium expression for this reaction, which by now we should be experts, products over reactants, bam, we got it. So this is our K for this reaction. Then what we're going to do is we're going to plug in all of these equilibrium values that we got from the ICE table. So for example, equilibrium concentration of HI is 2x, so that I put 2x there. I just plugged it in, I got 2x squared. And then in the bottom here, equilibrium concentration for H2 and I2 are 1 minus x and 2 minus x respectively. So I just plug those in. Now we're going to start distributing. So 2x squared is 4x, because remember you're distributing for both. 2x times 2x is 4x squared. And then here I use the distributive property, also known as foiling, or you can use the box method to multiply these two binomials to get this trinomial here. And I also plugged in my value for K already. So bam, we're good. Now, the next thing we need to do is we need to get rid of that fraction. To get rid of the fraction, we're going to use cross multiply. So basically, I'm going to multiply 1 minus 3x plus x squared. I'm going to multiply all of this with the 50.5. So I'm going to distribute the 50.5 to that. And that's what I got on this side. And then on the other side, I have the 4x squared. So I got rid of my fraction by cross multiplying. Cool. So now that all that's done, now how do we solve for x? Because we need to know what x is in order to plug it into these expressions. All right, well, you could use some factoring techniques, but T-chart, snowflake, and differences of squared only really work in certain cases. And most of the ones that you'll see this won't work for. So the easiest thing to do is just use the straight quadratic formula because it solves it automatically. And it's kind of simple once you get used to using it. So this is what we ended up with after we plugged in our equilibrium values and cross multiply to get rid of the fraction. We have this here. And the first thing I want to do to use the quadratic formula, before I use the quadratic formula, is set my equation equal to 0 by moving some terms over using inverse operations. In this case, I just chose to move the 4x over, so I subtracted both sides by 4x, and I get this equation. Now I have this equation set to equal to 0. Perfect. Okay, so if it's set equal to 0, I can go ahead and identify my values for a, b, and c by knowing that a is the coefficient in front of x squared, b is the coefficient in front of x, and c is the constant. Once I know those, I can go ahead and plug that into the quadratic formula. So in this case, for example, b is negative 151.5x. I would plug it in here and there. And a is 46.5. I would plug that in here, and c is 50.5, and I plug that in here. And that's what I got. One thing to note is since my b is negative, you got to keep the sign with it, negative 151.5, negative b would then be negative 151.5, so positive 151.5. All right, so once you have that plugged in, the next thing you want to do is you want to take care of all of this first. Do what's underneath the square root first, so square that, and then subtract whatever you get when you square that. You're going to subtract from that 4 times all of this. And then whatever the value is that you get under the square root, then you take the square root. It's also important to note that this is essentially 2 equations. It's going to be plus what's under the square root, and then plus the square root and minus the square root. So I sort of split that up. And what I got under the square root is 116.4. So I have 151.5 plus 116.4 all over 93, which is what I got when I do 2 times 46.5. And that gives me 2.9, x equals 2.9. And on the other hand, I have, for the equation where it's minus what's under the square root, I got 0.38. For every quadratic formula, you should get 2 solutions, unless the value under the square root is 0, in which case you would only get 1. But in this case, we have 2 solutions. So when you have 2 solutions, you got to pick which one is makes the most sense. And in our case, the one that makes the most sense is this one, because you'll see in a moment, this value for x is too large. When we go and try to plug that in, we would get a negative value for our equilibrium concentrations, and we don't want that. All right, so this is the value we're going to use for x. Okay, so going back here,